Hello there, and welcome to the Sleepy Space Channel. Far beyond the last planet, at the edge of our solar system, sits a structure so enormous that it surrounds the Sun and every world at once, and no one has ever seen it. It is called the Oort Cloud, a faint spherical shell of perhaps 1 trillion frozen bodies, marking the true outer boundary of the Sun's reach. We have never photographed it, never resolved a single one of its icy mountains, and yet nearly every astronomer is certain it is really out there. The reason we believe in it falls quietly out of the sky, in the form of comets that arrive from every direction at once. Tonight we will follow those comets back to their source and answer the two soft questions the dark keeps asking. How do we know it is there, and why can we not see it? If you find these slow journeys through space worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next couple of hours, none of this is yours to solve. Settle in. Let your shoulders soften. Let your breathing slow and lengthen. Let the day drift away from you, out past the planets, and into the calm and the dark. Let's begin. Part 1. The edge we cannot see. There is a structure at the edge of our solar system that no one has ever seen. It is the largest thing the Sun holds, and also the faintest. It surrounds the Sun and every planet, not as a flat ring, but as an immense hollow shell, enclosing everything we know, the way a sphere encloses its own center. Inside that shell sit the Sun, the 8 planets, the asteroid belt, the icy ring beyond Neptune, and the long dark gulf past all of them. The shell itself lies so far out that the Sun, seen from there, would be only the brightest star in a quiet sky. We call this shell the Oort Cloud. It is thought to be a reservoir of icy bodies, possibly numbering in the billions, possibly in the trillions, drifting at the outermost limit of the Sun's reach. And here is the strange part, the part worth sitting with for a moment before the night settles fully around it. We have never directly seen the Oort Cloud. Not with the largest telescope, not from the closest spacecraft, not once in all the centuries we have studied the sky. It has never appeared in any image. Everything we believe about it, we have inferred from clues. The way you might know a hill is there from the way the streams run down its sides. And yet, almost every astronomer accepts that it is real. The evidence is indirect, but it is consistent, and it is difficult to explain any other way. So the question that opens this long, quiet journey is twofold, and the whole night will turn on it. How do we know that something we have never seen is truly out there? And why, after all this time, have we never managed to see it at all? These are not unsettling questions. By the end of the night, they will feel like the opposite. But they are the doors through which we step out toward the edge. To begin, it helps to fix our sense of distance, because the ordinary numbers we use on Earth fail completely out here. The natural ruler for the solar system is the distance between the Earth and the Sun. That distance is about 150 million kilometers, and astronomers give it a simple name. They call it 1 astronomical unit. The Earth orbits at 1 astronomical unit from the Sun. It is the first rung on a ladder that climbs outward into the dark. Climb that ladder, and the planets fall behind quickly. Neptune, the outermost of the major planets, orbits at about 30 astronomical units, 30 times farther from the Sun than we are. Past Neptune lies the icy field of debris that supplies many of the comets we know, and it stretches outward to perhaps 50 astronomical units, with a thinner scattering reaching farther still. For most of human history, this was as far as our picture of the solar system went. The planets, a few belts of rubble, and then nothing. But the Oort Cloud lies far, far beyond all of that. Its inner edge is thought to begin somewhere near 2,000 astronomical units, already dozens of times farther out than Neptune. And its outer edge may reach 100,000 astronomical units or more, so distant that light itself, the fastest thing there is, would take well over a year to cross from the Sun to the cloud's far side. Laid end to end, the shell may be more than 1.5 light-years across. That makes everything else, every planet and belt and bright familiar world, a single small dot at the center of an enormous dark sphere. This is the scale we are dealing with tonight. The territory the Sun governs is mostly not the bright, crowded middle we picture when we think of the solar system. It is this immense, faint, frozen outer shell, silent and almost entirely empty, marking the true boundary of the Sun's domain. We have never seen it. We are fairly sure it is there. And over the next couple of hours, slowly and without any hurry, we are going to find out how both of those things can be true at once. It is worth pausing on what kind of object the Oort cloud actually is, because it does not resemble anything in our everyday experience. It is not a solid object, like a planet or a shell of metal. It is not even a continuous thing, like a cloud in the sky. It is a population, a scattering of separate frozen bodies, so numerous and so spread out that taken together, they form a roughly spherical region around the Sun. Calling it a cloud is a kindness of language. In truth, it is more like a swarm so thin that you could pass through it for years and never come near a single member. And yet, because the bodies share a common origin and a common region of space, astronomers treat them as one structure, one cloud, one outermost layer of the solar system. There is also the matter of why this cloud, and not the planets, marks the true boundary of the Sun's domain. We tend to think the solar system ends somewhere near the last planet, or perhaps a little beyond it. But a planet's orbit is not a wall. It is simply a path. The real question of where the solar system ends is a question of how far the Sun's gravity can hold something in orbit, and that reach extends far past the planets, all the way out to the cloud. The Oort cloud is not a far suburb of the solar system. It is the actual edge, the place where the Sun's grip finally loosens. Everything we usually picture as the solar system is only the lit interior of a far larger and darker whole. So, as the night begins, let go of the small, tidy picture of a few planets circling a star. Replace it with something much larger and much quieter. A small, bright center, and around it, reaching out more than a light year in every direction. A faint and frozen sphere that we have never seen, but are nearly certain is there. That sphere is the destination of this long, slow journey, and we will approach it the only way anyone ever has, not by looking, but by following the evidence outward, step by patient step, into the dark. There is one more thing to settle before we set out, and it is a matter of attitude as much as fact. The unseen edge of the solar system can be described in two very different tones. It can be made to sound eerie, a dark and secret structure lurking at the boundary of the known, vast and invisible, and faintly threatening. Or it can be described as it more truly is, a calm and ancient shell, the natural outer boundary of our home, no more menacing than the far wall of a quiet field at night. Tonight we choose the second tone, and we will keep it the whole way out. The Oort cloud is not a thing that hides from us in any sinister sense. It is simply far and faint and patient, and we are only now, with care and reason, coming to know it. The dark at the edge of the solar system is a gentle dark, and there is nothing in it that wishes us anything at all. Part 2. The belts we can see and the one we cannot. Before we go all the way out to the unseen shell, it helps to stand on ground we already understand. The solar system has two regions of leftover debris that we can observe directly, and knowing them makes the third, hidden one, far easier to picture. Both of these known regions are flat. Both lie roughly in the same plane as the planets, like rings laid on a tabletop. And both orbit in the same direction the planets travel, smoothly and predictably, leftovers from the building of the worlds. The nearer of the two sits between Mars and Jupiter. It is a broad ring of rocky bodies, the asteroid belt, holding everything from grains of dust to bodies hundreds of kilometers across. It is close enough to the Sun that its members are warm and rocky, and bright enough to catch sunlight and send a little of it back to us. That reflected light is the reason we can study the asteroid belt directly. Telescopes can pick out individual asteroids, track their orbits, and watch them turn. There is no mystery about whether the asteroid belt exists. We can simply look at it. Farther out, past Neptune, lies the second ring. It is a donut-shaped field of icy bodies rather than rocky ones, a frozen band circling the outer solar system. It was proposed generations ago as the source of a particular family of comets, the short-period comets, the ones that return on schedules we can predict. This icy belt begins near Neptune's orbit and extends outward, its main body reaching to around 50 astronomical units, with a thinner, scattered population trailing much farther into the dark. The most famous resident of this belt is a small world that once counted among the planets, a frozen sphere, far dimmer and colder than anything in the inner solar system. Now and then, gravity gives one of these icy bodies a nudge, tipping it onto a new path that carries it closer to the Sun. As it warms, it grows a glowing head and a tail, and a new short-period comet is born. These comets keep orbits shorter than 200 years, and because they travel roughly in the plane of the planets, their returns can be calculated and anticipated. They are the comets we have learned to expect. So we have two debris rings, both flat, both in the plane of the planets, both close enough to see. Hold that picture clearly, because the Oort Cloud is the opposite of it in every way that matters. It is not flat, it is a sphere. It does not lie in the plane of the planets. It surrounds them on every side, above and below, as much as around. And it is not close enough to see. It lies so far out and so dark that no telescope has ever resolved a single one of its bodies. The two belts we know are the stepping stones. They are the familiar shoreline. The Oort Cloud is the immense, faint ocean that begins where the known map runs out. The difference is not only one of distance, it is one of shape, and that difference holds a clue. A flat belt can only produce comets that travel more or less in the plane of the planets, because that is the only place its members are. If every comet behaved that way, two flat belts would be enough to explain them, and there would be no need to imagine anything more. But the comets do not all behave that way. Some of them arrive from completely the wrong direction, falling toward the Sun from above the planets, or below them, or sideways, on paths that no flat ring could ever produce. Those comets are the loose thread. And in the next part, we begin to pull on it. There is a further reason the two known belts make such useful stepping stones, and it concerns how we learned to think about leftover material at all. For a long time, the planets were the whole story. The solar system was imagined as the Sun and its worlds, and the spaces between were thought to be simply empty. The discovery that broad regions of debris orbit alongside the planets changed that picture. It taught us that the building of the planets was not tidy, that it left behind enormous quantities of rubble, and that this rubble settled into structured regions rather than simply vanishing. Once you accept that the inner solar system holds a belt of rocky leftovers, and the outer solar system holds a belt of icy ones, the idea of yet another, far larger reservoir of leftovers at the very edge becomes much easier to entertain. It also helps to notice what the two belts have in common, because the Oort cloud breaks every one of those shared traits. Both belts are flat, lying close to the plane of the planets. Both orbit in the same direction the planets do. Both are made of bodies on relatively ordinary, roughly circular paths that keep them at fairly steady distances from the Sun. And both are close enough that sunlight still reaches them with real strength, lighting their members for our telescopes to find. The Oort cloud, by contrast, is spherical rather than flat, holds bodies on wildly stretched and randomly tilted orbits, and lies so far out that sunlight arrives only as the faintest whisper. The belts are the rule. The cloud is the grand exception, and the exception is what we are traveling toward. One more thought about the icy belt beyond Neptune deserves a place here, because it sits between the familiar and the unknown. That belt is not perfectly sharp-edged. Its main, denser body gives way to a thinner, more scattered population that trails outward to far greater distances on more stretched and tilted orbits. In that scattered outer fringe, we begin to see hints of the kind of behavior that becomes the rule in the Oort cloud, bodies on long, eccentric paths, loosened from the orderly plane. The transition from the belts we can see to the cloud we cannot is not a sudden jump, but a slow fading outward, the orderly giving way, by degrees, to the immense and the dark. There is a pleasing logic to building our understanding outward in layers like this, from the rocky belt to the icy belt to the distant cloud, because it mirrors the way our knowledge actually grew. We came to know the nearer belt first, then the farther one, then, only later, and only by inference, the cloud beyond them. Each layer prepared us to imagine the next. Having accepted a ring of rock between Mars and Jupiter, we could accept a ring of ice past Neptune. Having accepted a ring of ice past Neptune, we could accept, at last, the idea of a sphere of ice surrounding everything, far beyond. The solar system revealed its outer structure to us patiently, one shell at a time, each new layer larger and fainter and stranger than the one before, until the picture reached all the way out to the dark and spherical edge. Part 3. The comets that arrive from everywhere. Comets, it turns out, come in two very different families, and the difference between them is the first real evidence that something enormous waits at the edge of the solar system. The first family we have already met. These are the short-period comets, the predictable ones, returning in less than 200 years, traveling roughly in the plane of the planets, tied to the icy belt beyond Neptune. They are the regulars. We know their schedules, and we can wait for them. The second family is altogether stranger. These are the long-period comets, and almost everything about them runs counter to the first family. Their orbits are not measured in decades or centuries, but in thousands of years, in tens of thousands, in some cases, in millions. A single trip around the Sun, out to the farthest point and back, can take a long-period comet, longer than our entire species has existed. Many of them have been seen only once in all of recorded history. They fall in from the dark, round the Sun once, and depart on orbits so immense that they will not return for ages, long after everything alive today is gone. And then there is the matter of direction. The short-period comets keep to the plane of the planets, like traffic on a single broad road. The long-period comets obey no such rule. They arrive from every direction in the sky at once. Some come in from far above the plane of the planets, some from far below, some at every angle in between. Some orbit the Sun in the same direction the planets do. Others fall in completely backward, against the grain of everything else in the solar system. there is no preferred direction at all. If you charted where the long-period comets came from, you would find them spread evenly across the entire sphere of the sky. This is the quiet fact that demands an explanation. A flat ring of debris simply cannot send comets in from every direction. Whatever the long-period comets are falling out of, it cannot be flat. It has to surround the solar system on all sides, above and below as fully as around the middle. It has to be a shell. The very randomness of their arrival is the shape of their source, written across the sky. There is a second clue hidden in these comets, and it concerns not their direction, but their distance. When a long-period comet falls toward the Sun, its orbit can be measured, and from that orbit astronomers can work out the farthest point the comet reaches before it turns and falls back. That farthest point is the clue to where the comet came from. A comet that merely passes through from interstellar space would behave one way. A comet bound to the Sun, falling in from a great distance and destined to return, would behave another. And when the long-period comets were measured, they showed clearly that they were bound to the Sun. They were not visitors from beyond. They belonged to the solar system, falling in from somewhere far out within the Sun's own territory. So the long-period comets gave us two pieces of a puzzle. First, they come from every direction, which means their source is a sphere wrapped around the solar system. Second, they are bound to the Sun, which means that sphere lies within the Sun's reach rather than out in the space between the stars. The only thing left to determine was how far out the sphere actually lay. And the answer to that, when it came, was so large that it reshaped our entire sense of where the solar system ends. That is the thread we follow next, into the careful reading of the orbits that first revealed the cloud. To feel how strange the long-period comets truly are, it helps to dwell for a moment on the spans of time involved, because they are unlike anything in ordinary life. A short-period comet might return every few decades, within a single human lifetime, so that a person could see it as a child and again as an elder. The long-period comets are nothing like this. Their orbits can take many thousands of years to complete, and the longest of them stretch into the millions of years. A comet falling toward us now, blazing briefly in the sky, may have last passed this way before our species had learned to speak, and may not pass again until long after every language now spoken has been forgotten. Each long-period comet is, in effect, a once in the history of civilization visitor, and most of them only once, even in that. This immense range of orbital periods also tells us something about the cloud itself. A comet with an orbit of a few thousand years comes from the nearer parts of the cloud. A comet with an orbit of millions of years comes from far out toward its dim outer edge. By collecting comets of many different periods, astronomers effectively sample the cloud at many different depths, building up a picture of a reservoir that extends across an enormous range of distances, rather than sitting at a single radius. The variety in the comet's orbits is the variety in the cloud's own structure, written out in the sky for anyone patient enough to read it. And there is a quieter point hidden in the unpredictability of these comets. Because they arrive from every direction and on schedules too long to anticipate, each one comes as a kind of surprise, a body appearing seemingly out of nowhere, brightening as it nears the Sun. For most of history, such comets were mysteries, their origins entirely unknown, their appearances unexplained. The realization that they all come from a single distant shell surrounding the solar system turned that mystery into something orderly and understandable. The comets did not come from nowhere after all. They came from the edge, every one of them, falling inward from the same faint sphere, and the apparent chaos of their arrivals turned out to be the signature of a single calm and enormous source. There is a further quiet detail in how these comets behave that is worth noticing. Because a long-period comet is making, in many cases, its very first approach to the Sun, it often arrives more brilliant and more active than the comets we are used to. The ices on its surface have never been warmed before, never been driven off by an earlier passage. So when such a comet finally nears the Sun, it can release its frozen material vigorously, blooming into a particularly bright and beautiful display. Some of the most memorable comets in human history have been exactly these first-time visitors from the cloud, bodies that had waited frozen and untouched for the whole age of the solar system before making a single dazzling appearance. Their brilliance is, in a sense, the brilliance of something happening for the first and only time, a frozen body spending in one bright season the patience it gathered across billions of years. Part 4. Reading the orbits. The discovery of the Oort Cloud is not a story of someone seeing it. No one ever did. It is a story of someone reading it, deducing an unseen structure from numbers alone, the way a careful mind can sense a shape in the dark by the way things move around it. The reading came down to a single measurement repeated across many comets, and the pattern that emerged from those measurements. The measurement is the farthest point in a comet's orbit, the place where it sits at its greatest distance from the Sun before gravity turns it around and pulls it back inward. For an incoming long-period comet, that farthest point is a kind of return address. It marks, roughly, how far out the comet was before it began its long fall toward us. Measure that distance for one comet, and you learn where one comet came from. Measure it for many comets, and you can begin to see whether they share a common home. When astronomers gathered the long-period comets and worked out the farthest point of each one, they did not find the distances scattered randomly across every possible value. They found them clustered. A large share of the long-period comets had their farthest points grouped around a single, enormous distance, on the order of tens of thousands of astronomical units, a figure often placed near 50,000 astronomical units from the Sun. That clustering was the decisive clue. It was as though many different travelers, arriving from many different directions, all turned out to have set out from roughly the same faraway altitude. Such a thing does not happen by accident. It points to a shared reservoir at that distance, quietly releasing comets inward across the ages. Put the pieces together, and a single picture falls into place. The long-period comets are bound to the Sun, so their source lies within the Sun's territory. They arrive from every direction, so their source is a sphere surrounding the solar system rather than a flat ring. And their farthest points cluster around tens of thousands of astronomical units, so that sphere lies at an immense distance, far beyond the planets and the known belts. 3 independent facts, each pointing to the same conclusion. A roughly spherical swarm of icy bodies surrounding the solar system at a great distance, slowly feeding comets into the inner system. That swarm is the Oort Cloud. What is remarkable is how well this idea has held up. In the years since it was first proposed, careful mathematical models of how comets would be stored at such distances and how they would be dislodged and sent inward have agreed closely with what we actually observe. The numbers of long-period comets, the spread of their orbits, the way they arrive across the whole sky, all of it fits a distant spherical reservoir. The cloud was proposed to solve one puzzle, the origin of the long-period comets, and it went on to fit a great deal more than the single puzzle it was built for. That is usually a sign, in science, that an idea is touching something true. And still, it is worth repeating, because it is the gentle paradox at the center of this night. All of this was deduced. The cloud was read out of the motions of falling comets and confirmed by the agreement of models, but it was never seen. We are as confident of the Oort Cloud as we are of many things we can photograph, and we hold that confidence entirely on the strength of indirect evidence. There is something calming in that, once you sit with it. It means the universe is knowable even where it is invisible, that patience and careful attention can reach out past the limit of sight and feel the shape of something enormous and dark. We did not need to see the cloud to know it was there. The comets told us, one slow arrival at a time. It is worth lingering on just how much can be learned from an orbit, because this is the quiet method at the very center of the whole discovery. A comet's path through space, once measured carefully over a series of nights, is not merely a record of where the comet is. It is a record of where it has been and where it is going, stretching backward and forward in time, far beyond the brief window in which we actually watch it. From a short arc of observed motion, the full shape of the orbit can be reconstructed, including the farthest point the comet reaches, even though we never see the comet anywhere near that distant point. We watch a comet for a few weeks near the Sun, and from that alone we can say how far out into the dark it began its fall. The cloud was found in exactly this way. By reading the far ends of orbits we could only observe near their near ends. There is also a subtle but important distinction in the orbits that strengthen the case for the cloud. When a long-period comet first falls inward, its orbit reflects where it truly came from. But after a comet has passed through the inner solar system once, the gravity of the giant planets can alter its path, shortening or lengthening its orbit for future passes. Astronomers learned to tell the difference between a comet making its first plunge from the distant cloud and one that had been through before. The comets on their very first passage proved especially telling, for their orbits pointed most cleanly back to that characteristic distance of tens of thousands of astronomical units. The freshest arrivals, the ones falling in for the first time, carried the clearest return address of all, and that address was the Oort Cloud. Finally, it is worth honoring the sheer patience and imagination the discovery required. No one flew out to the cloud. No one saw a single one of its bodies. The entire structure was conjured into our understanding from columns of numbers describing the paths of comets, combined with a willingness to ask what kind of source could produce such paths. It is one of the purest examples of reasoning reaching past the limit of sight, of the mind building a true picture of something invisible from the faint traces it leaves behind. The Oort Cloud began not as an observation, but as an act of careful thought, and the decades since have only strengthened the case. There is something deeply reassuring in that, in the idea that the universe yields its shape to patient attention, even in the places we cannot see. Part 5. The shape and size of the cloud. Having found the cloud in the motions of the comets, we can now try to picture it as it is thought to be. And the modern picture is not quite a single, simple shell. It is two regions that blend into one another, each with a slightly different shape, together making up the whole. The inner region lies closer to the Sun, and it is believed to be denser and somewhat flattened, closer to a thick disk than a true sphere. It still carries a faint memory of the flat plane that its bodies were originally scattered from, the plane of the planets. This inner region may hold more bodies than the outer one, and because it sits a little nearer the Sun's gravity holds it more firmly. It is the more stable, more settled portion of the cloud, less easily disturbed by anything passing by. Beyond it, the cloud opens out into the great spherical shell that most people imagine when they hear its name. This outer region surrounds the solar system evenly in all directions, above and below and around, a faint, enormous bubble of icy bodies. Out here, at the very limit of the Sun's reach, the Sun's hold is at its weakest. These outermost bodies are the most loosely bound of anything that still belongs to the Sun, and the most easily nudged by the gentle forces that reach in from the wider galaxy. The inner region remembers the disk it came from. The outer region has been stirred into a sphere. The sizes involved are difficult to hold in the mind, but they are worth stating plainly. The inner edge of the cloud is often placed around 2,000 astronomical units from the Sun. The outer edge is commonly placed near 100,000 astronomical units, and some estimates reach farther still. From one side to the other, the cloud may span more than 1.5 light-years. That is a meaningful fraction of the distance to the very nearest star beyond the Sun, which lies a little over 4 light-years away. To say it another way, the Oort Cloud is by far the largest structure that belongs to the Sun. The planets, the asteroid belt, the icy ring beyond Neptune, all the worlds we have ever named and mapped, together occupy only the tiny bright middle of the Sun's true domain. If you could pull back far enough to take in the whole thing at once, the planetary system would shrink to a single glinting point, and around it, immense and dark, would be the faint sphere of the cloud. Everything familiar is the center. The cloud is almost all of the rest. It is a curious feeling to learn that the part of the solar system we know best is the smallest part of it, and that the largest part is the part we have never seen. But there is a kind of comfort in that proportion. The bright, crowded middle, with its planets and its sunlight, is wrapped on every side by this enormous quiet shell, a calm outer boundary that has surrounded the worlds for as long as they have existed. The solar system is not a small lit room with darkness pressing at its edges. It is a small lit center held within a great gentle sphere, and the sphere is part of the home. The blending of the two regions, the flatter inner part and the spherical outer part, is worth picturing slowly, because it reveals how the cloud holds the memory of its own making. Close to the Sun, where the Sun's gravity is firmer, the bodies have kept more of the orderly arrangement they were born with, lying nearer the plane of the planets and moving on somewhat steadier paths. Farther out, where the Sun's hold is faint and the gentle pull of the galaxy and passing stars has had billions of years to work, the bodies have been lifted and tilted in every direction until any trace of the original plane has been smoothed away into a full sphere. So the cloud is not uniform. It is densest and flattest within, thinning and rounding as it reaches outward, until at its dim outer limit it becomes a true shell, surrounding the solar system on all sides. This structure also helps explain why the cloud is such a steady supplier of comets across the entire age of the solar system. The inner region, being more tightly held, is a stable, well-protected store, slow to give up its bodies. The outer region, being loosely bound, is more easily stirred, more readily nudged into sending comets inward. Together, they act like a reservoir with a deep, protected center and a sensitive outer surface, the surface releasing comets when disturbed, while the center holds its reserves in trust for the ages to come. The cloud does not empty quickly. It releases its bodies a trickle at a time, drawing first on its exposed outer layers, with vast reserves held safely deeper in. There is a humbling exercise in trying to hold the proportions honestly. If you imagined the orbit of Neptune shrunk down to the size of a coin, the Oort Cloud's outer edge would lie not on the same table, nor in the same room, but a good distance down the street. The planets, on that scale, would be a microscopic glinting speck. Nearly the whole of the solar system, by extent, is the dark and faint outer shell, and only the tiniest fraction is the bright, familiar realm of the worlds. We live, all of us, in that small, bright speck, wrapped around on every side by a sphere so large that our entire planetary system is lost within it, like a single mote of dust at the center of an enormous room. It is also worth noticing how gently the cloud's boundaries blur, because there are no sharp lines anywhere in this picture. The inner edge of the cloud is not a wall, but a gradual thickening, where the scattered bodies of the outer solar system slowly give way to the denser inner cloud. The transition from the flatter inner region to the spherical outer region is itself a gradual one, the bodies tilting more and more freely the farther out they lie. And the outer edge is the faintest fade of all, the cloud simply thinning away into the surrounding dark until there is nothing left to call part of it. Every boundary in the Oort cloud is a slow fading rather than a hard line. The whole structure is soft-edged, blurred, and gradual, more like a mist that thins at its margins than like anything with a definite surface. Even its limits are gentle. Part 6. How far is far? Numbers can wash over the mind without leaving a mark, especially numbers this large, so it is worth slowing down and trying to truly feel the distance to the Oort cloud. There are a few ways to do it, and each one stretches the imagination a little further than the last. Begin with light, the fastest thing in the universe. Nothing travels faster than light. And on Earth, it seems instant, crossing a room before we can register it. Yet even light takes time to cross the solar system. Sunlight reaches the Earth in about 8 minutes, so the sun you see is always 8 minutes old. That same sunlight takes about 4 hours to reach Neptune at the outer edge of the planets. To reach the inner edge of the Oort cloud, sunlight would have to travel not for minutes or hours, but for many days. And to reach the outer edge of the cloud, light would travel for well over a year. The cloud is so far out that the sun's own light grows old crossing the gap to it. Now think about how fast we ourselves have ever traveled. The most distant spacecraft humanity has ever launched have been flying outward for decades, moving at tens of thousands of kilometers per hour, far faster than any rocket near the Earth. After all those years of travel, these craft have reached only a little more than 100 astronomical units from the Sun. They have passed the planets. They have crossed out of the Sun's wind into the space between the stars. And they are still nowhere near the Oort cloud. They have not even begun to approach its inner edge. Carry that pace forward, and the scale becomes almost unbearable to picture, though in the gentlest way. A spacecraft moving at that tremendous speed would need something like 300 years simply to reach the inner edge of the Oort cloud. And then, to cross all the way through the cloud to its far side, it would need something on the order of 30,000 years more. 30,000 years is longer than all of recorded human history, several times over. The cloud is so wide that to fly across it would take longer than the entire span of human civilization, again and again and again. And yet, here is the part that turns the whole picture quiet. For all that size, the Oort cloud is almost entirely empty. Even if it holds 1 trillion bodies, those bodies are spread through such an enormous volume of space that they are extraordinarily far apart. A typical gap between one icy body and its nearest neighbor may be tens of millions of kilometers, farther than the distance between some of the planets. If you were somehow placed inside the Oort cloud, you would almost certainly see nothing nearby at all. No swarm, no field of ice, no crowding. Just the same scattering of distant stars you see from Earth, and the sun reduced to the brightest of them, and otherwise the long, even dark. So the cloud is colossal and faint at the same time, immense in reach and feather-light in substance. It is less a wall of ice than an idea of a boundary, a region so thinly populated that crossing it would feel like crossing ordinary empty space. That emptiness is part of why we cannot see it, a point we will come back to. But it is also part of its peace. The edge of the solar system is not a crowded or violent place. It is the quietest, emptiest, most patient region the sun governs. Another way to feel the distance is to think about how long it would take a message to cross it, because even our fastest signals are bound by the speed of light. A radio command sent to a spacecraft out past the planets already takes many hours to arrive, so that controllers must send an instruction and then wait half a day or more to learn whether it was received. If we somehow had a craft sitting at the inner edge of the Oort Cloud and wished to send it a message, we would send the signal and then wait, not for hours, but for many days, for that single message to cross the gap at the speed of light. And a message to the outer edge of the cloud would take more than a year to arrive, with another year for any reply. Conversation across the cloud, at the fastest speed the universe permits, would be measured in years. It also helps to set the cloud against the distance to the nearest star, because the two are surprisingly close in scale. The nearest star beyond the Sun lies a little more than 4 light-years away. The outer edge of the Oort Cloud may reach more than 1.5 light-years from the Sun. That means our cloud already extends a good fraction of the way toward our nearest neighbor. The dark between the stars is not nearly as empty of the Sun's influence as it first appears. The Sun's domain reaches out so far that, in a sense, there is no clean gap of truly empty space before the next star begins. The realms of the stars come close to touching across the dark. And yet, for all this almost unbearable distance, it is important not to let the scale feel cold or frightening. The bigness of the cloud is not a bigness of danger. Nothing out there is rushing toward us. Nothing out there is waiting to do us harm. The immense distances simply mean that the cloud is profoundly remote and profoundly slow, a place where nothing happens quickly and almost nothing happens at all. To contemplate the size of the Oort Cloud is not to feel small in a fearful way. It is to feel held within something far larger and far calmer than ourselves, a structure so patient that the entire span of human history is, to it, the briefest of moments. There is rest in a scale like that, once you stop trying to grasp it all at once and simply let it be large. It can be steadying, rather than dizzying, to hold these distances loosely, instead of trying to seize them all at once. The mind is not built to truly grasp 100,000 times the distance from the Earth to the Sun, and there is no need to force it. It is enough to understand the shape of the truth, that the cloud is enormously, almost unthinkably far away, that light itself grows old crossing to it, that our fastest craft would need tens of thousands of years to pass through it. The exact figures matter to the astronomers who model the cloud, but for the rest of us, the feeling is what counts, and the feeling is one of immensity, held at a calm distance. The cloud is far enough that nothing about it presses upon us. It is simply, peacefully, very far away, and that distance is a kind of quiet all its own. Part 7. What the bodies actually are. It is one thing to speak of a cloud of icy bodies, and another to picture what a single one of them is actually like. So let us bring one close in the mind, even though no one has ever truly seen one out in the cloud. The bodies of the Oort Cloud are best thought of as cometary nuclei in cold storage, the frozen seeds from which comets grow. A typical one might be a few kilometers across, roughly the size of a large mountain on Earth. Some are smaller, mere hills of ice. A few rare ones are much larger, tens or even more than 100 kilometers across, true small worlds. But the ordinary member of the cloud is mountain-sized, a single dark lump drifting alone in the cold. It is not a planet, and not quite an asteroid. It is something in between, a mixture of ice and dust held loosely together. The ice is not only frozen water, though water ice is part of it. These bodies also hold frozen carbon dioxide, frozen carbon monoxide, frozen methane and ammonia, a whole pantry of ices that on Earth would be gases. Mixed through the ice is rocky dust, fine dark grains left over from the building of the solar system. The old description of a comet as a dirty snowball captures the idea well enough, a clump of various ices threaded with grit. Some are perhaps better described as icy dirt balls, more dust than ice, but the spirit is the same. They are frozen, fragile, and very, very old. Out at the cloud's distance, these bodies receive almost no warmth. The sun, so dominant and bright from where we stand, is just a point of light out there, no warmer to the touch than any other star. With no real heat reaching them, the bodies stay deep frozen and utterly inert. They have no tails, no glowing heads, no motion that the eye could follow. They are simply dark, cold, and still, drifting along their immense slow orbits in silence. A body in the Oort Cloud is not a comet yet. It is only a comet waiting to happen, and most of them will wait forever, never once falling close enough to the sun to come alive. The total number of these bodies is genuinely staggering, even if the exact figure is uncertain. Estimates run into the billions and the trillions. The combined mass is harder to pin down, and different methods give different answers, but the sheer count of objects is beyond easy imagining. 1 trillion mountains of ice, each one alone in the dark, each one tens of millions of kilometers from its nearest neighbor, all of them turning slowly around a sun so distant it gives them no warmth. That is the population of the cloud. There is one more thing worth saying about these bodies, and it matters for how we feel about them. They are not strange or alien material. They are leftovers, the same icy building blocks that helped form the outer planets, simply flung to the edge and abandoned in the cold rather than gathered into a world. The edge of the solar system is paved with the same substance as its beginning. The frozen bodies of the cloud are siblings of the giant planets, made of the same stuff at the same time, and only chance decided which became part of a world and which drifted out to wait at the boundary. There is a quiet kinship in that, between the worlds at the center and the dark bodies at the rim. It is worth dwelling on the deep cold of these bodies, because that cold is the reason they have endured. Out in the cloud, the temperature is only a handful of degrees above the coldest temperature anything can reach, the absolute floor below which nothing can be chilled. At such temperatures, the ices are rock hard and utterly stable. Nothing melts. Nothing flows. Chemical changes that would happen quickly in a warmer place slow nearly to a stop. A body out there is locked in a kind of perfect stillness, its substance frozen exactly as it was when the body first formed. The cold is not a threat to these bodies. It is what preserves them, the reason they can serve as faithful samples of the distant past. The fragility of these bodies is also worth understanding, because it shapes what happens when one of them finally falls toward the sun. They are not solid stone. They are loose, porous mixtures of ice and dust, held together weakly, more like packed snow than like rock. This is why a comet can grow such an enormous glowing head and such long tails from so small a body. The warming sun does not need to melt solid rock. It needs only to coax the loosely held ices into vapor, and they readily oblige, streaming off the fragile body and carrying dust with them. It is also why some comets crumble or break apart entirely as they round the sun. The bodies of the cloud are delicate things, and they were built to last only in the cold and the dark, not in the warmth and the light. There is a quiet dignity in imagining the solitude of a single one of these bodies. Picture one mountain of ice, alone, at the edge of the sun's reach. Its nearest neighbor is so far away that even if both were lit, neither could see the other. Around it, the sun is a bright point among the scattered stars, giving no warmth. It has drifted in this silence for more than 4 billion years, tracing an orbit so large that it has completed only a handful of circuits, or perhaps only one in all that time. It does nothing. It waits. And it may wait forever, or it may, after billions of years of stillness, feel the faint tug that begins its long fall toward the light. There are perhaps 1 trillion such bodies, each one keeping its own solitary vigil at the edge of everything, and together they make the quietest population in the solar system. It is worth holding in mind, too, that these bodies are not lifeless in any sad sense, but rather perfectly at rest. We sometimes speak of the cold and dark as if they were bleak, but for an Oort Cloud body, the cold and dark are simply home, the conditions under which it can endure unchanged for the entire age of the solar system. There is nothing broken or forlorn about a frozen body at the edge. It is exactly as it should be, exactly where the physics of the system placed it, doing exactly what such a body does, which is to wait in stillness. If we could visit one, we would find not a ruin, but something pristine, a clean and ancient body of ice and dust, untouched and complete, keeping its long and patient watch at the boundary of the sun's reach. The peace of these bodies is not emptiness. It is wholeness, held in the cold. Part 8. How the cloud was made. If the cloud was never seen, and only deduced, then how it formed is an even deeper layer of inference, a story reconstructed from physics and from the cloud's own shape. But the leading explanation is elegant, and it ties the faint outer shell directly to the birth of the planets themselves, more than 4 billion years ago. In the beginning, the young solar system was not the orderly place it is now. Around the new sun spun a broad disk of gas and dust, and within that disk, countless small bodies were taking shape, the building blocks of planets. As the giant planets grew, the space around them was still littered with smaller leftover bodies, icy chunks that had not been swept up into any world. The solar system was crowded with this rubble, far more than remains today. The giant planets, with their enormous gravity, went to work on that rubble, though not gently and not all at once. Each time one of these small, icy bodies passed near a giant planet, the planet's gravity flung it onto a new path, like a slow gravitational sling. Some of the bodies were thrown inward, toward the sun. Some were thrown clean out of the solar system entirely, lost forever to the space between the stars. But a great many were flung outward onto enormously stretched orbits, paths that carried them far beyond the planets and then back again, out to distances of thousands and tens of thousands of astronomical units. And here is where the wider galaxy entered the story. At the far ends of those stretched orbits, so distant from the sun, the bodies came within reach of forces from outside the solar system. The gentle pull of stars passing in the distance and the broad, slow tide of the galaxy itself began to act on them. These outside forces did something crucial. They lifted the far ends of the orbits and rounded them out, detaching the bodies from the giant planets that had thrown them. No longer did the bodies dive back into the planetary region on each orbit. Instead, they were lofted into long, stable, lonely paths that kept them out at the edge, no longer interacting with the planets at all. Over an immense span of time, this process repeated for body after body, until a great population of icy chunks had been parked at the edge of the sun's reach. And as they were lifted and reshaped, their orbital tilts were gradually randomized, scattered away from the original flat plane into every possible angle. The flat scattering of the early planetary region was slowly stirred into a sphere. The bodies closest in kept more of their original flattening, which is why the inner cloud is more disc-like. The bodies farthest out were stirred completely, which is why the outer cloud is a true shell. The shape of the cloud, in other words, is a record of how it was made. It is a strange and beautiful origin when you sit with it. The faint shell at the edge of the solar system is built from the very same material as the planets, cast outward in the chaos of the system's youth, and then gently caught and held at the boundary by the combined pull of the sun, the passing stars, and the galaxy. The cloud is the solar system's discarded beginning, preserved at its outermost limit. Everything that did not become a world drifted out to become the edge. And there it has stayed, almost unchanged, ever since. The role of the giant planets in this story deserves a closer look because it reveals a kind of cooperation between the worlds and the edge. The giant planets were the engines of the scattering. Their great mass and gravity gave them the power to take a small, icy body on a close pass and hurl it onto an entirely new path, adding or removing enough energy to send it far outward. Without such massive planets, there would have been no efficient way to fling the leftover bodies to the distances where the cloud now lies. So the existence of the Oort Cloud is bound up with the existence of the giant planets. The same worlds that dominate the middle of the solar system are the ones that built its outer edge, casting their leftover siblings outward into the dark. It is also worth understanding why the help of the wider galaxy was necessary, and not merely incidental. A body flung outward by a giant planet, if left to the planets alone, would simply fall back inward on its next orbit and risk being flung again, or thrown out of the solar system entirely, or dropped back toward the sun. The orbits would never settle. What allowed the cloud to form and last was that, at the far ends of those stretched orbits, the gentle outside forces lifted the body's closest approach away from the planets, so that they no longer returned to be flung again. In effect, the galaxy reached in and gently set the bodies down at a safe distance, beyond the reach of the planets that had thrown them. The planets did the throwing, and the galaxy did the catching, and between the two of them the cloud was assembled. There is a long, slow grandeur to imagining this process unfolding across the ages. It did not happen in a moment. Across many millions of years, body after body was flung outward and gently caught, the cloud filling gradually, like a tide coming in one wave at a time. The orbital tilts were randomized a little more with each passing influence. The flat scattering stirred slowly toward a sphere. By the time the process had run its course, a structure larger than anything else in the solar system had been built at its edge, entirely out of the discarded scraps of planet building, held in place by the combined and patient pull of the sun, the stars, and the galaxy. The cloud is the long, quiet result of the solar system tidying its own beginnings, sweeping its leftover material out to the edge and leaving it there, frozen and still for the rest of time. Part 9. The time capsule at the edge. There is a reason astronomers care so much about a structure they cannot see, beyond the simple pleasure of solving where the comets come from. The Oort Cloud is, in a real sense, a museum of the early solar system, kept in perfect cold storage at the edge of the dark. Think about what it means for these bodies to have drifted so far from the sun for so long. Out at the cloud's distance, there is almost no warmth, almost no light, and almost nothing to disturb them. The bodies have not been baked by the sun, ground down by collisions, or reshaped by the pull of nearby worlds. They have simply drifted, frozen, and untouched since the time the planets were forming. The material they are made of is very nearly the same material that filled the young solar system more than 4 billion years ago. Nothing out there has had the chance to change it. That makes each body a kind of frozen sample of the beginning, a small parcel of the original ingredients, sealed away in the cold and held without alteration across the entire age of the solar system. While the inner worlds were melting, colliding, building atmospheres, and weathering away, the bodies of the Oort Cloud were doing nothing at all. They were keeping still, and in their stillness, they kept faith with the past. This is why a long-period comet is such a precious thing when one finally falls inward. When it nears the sun and begins to warm, it releases gas and dust that have been locked away since before the Earth had a solid surface. For a few weeks or months, that ancient material streams out into space where it can be studied, and we get to examine a piece of the early solar system without having to travel back in time to find it. The comet brings the past to us, carrying it inward from the edge. So the cloud is not only a boundary and a reservoir. It is an archive. Every dark body out there is a page from the solar system's first chapter, preserved exactly as it was written, waiting in the cold. And once in a long while, the galaxy reaches in, loosens a single page, and lets it drift down toward the sun, where for a brief season it can be read. There is something gentle in that thought. The farthest, coldest, most untouched part of the solar system is also the part most faithful to its origin. The edge is not a ruin or a wasteland. It is a memory, kept perfectly, in the dark. The idea of the cloud as an archive becomes richer when you consider what exactly is being preserved. The bodies hold not only frozen water, but a whole mixture of frozen gases, the very substances that filled the cold outer parts of the young solar system. In a warmer place, these volatile ices would long ago have escaped into space, leaving only rock behind. The inner worlds, including the Earth, lost most of their original light ices in just this way, baked off by the nearby sun. But out in the cloud, where there is no warmth, the bodies kept everything. They are among the few places in the solar system where the original light, volatile material still survives in its first state, untouched by heat. To study a long-period comet is to study a chemistry that has otherwise vanished from the inner system entirely. This is also why comets have long been linked, in our thinking, to the deeper history of the Earth and even of life. The icy bodies of the outer solar system carry water and simple carbon-bearing compounds, the same kinds of ingredients that the young Earth would have needed. Whether or not comets delivered a meaningful share of Earth's water, the bodies of the cloud are made of the sort of material from which worlds and their oceans are built. There is a kinship between the frozen bodies at the edge and the living world at the center, a shared inheritance of the same primordial ices. The cloud holds, in deep freeze, a version of the raw material that the inner solar system long ago transformed into rock and water and air. There is a gentle reframing in all of this, worth carrying into the quiet of the night. We tend to think of the edge of the solar system as the place where things end, the last cold margin before the true emptiness of interstellar space. But the cloud invites the opposite view. The edge is where the beginning is kept. The freshest, most original, most untouched material of the entire solar system is not at its busy, warm center, but at its dark, cold rim, held in perfect stillness for billions of years. The edge is not where the story runs out. It is where the first page is stored, unchanged, waiting in the cold, ready to be read whenever a single body finally falls toward the light. There is a particular kind of stillness worth imagining here, the stillness of something that has kept faith with the past simply by remaining unchanged. The inner worlds are restless places, forever reshaping themselves, erasing their own histories as they go. The Earth has melted and folded and weathered away nearly all trace of its earliest days. But the bodies of the cloud have done none of this. They have simply held still, in the cold and the dark, for the entire age of the solar system, and in holding still they have kept a record that the busy inner worlds long ago lost. There is a lesson in that, gentle enough for the end of a long day. Sometimes the most faithful keeper of a beginning is the thing that did the least, that stayed quiet and cold and still while everything else rushed to change. The edge of the solar system remembers its origin precisely because, out there, nothing ever happens. Part 10. The slow stirring. A body left entirely alone in the Oort Cloud would never become a comet. It would simply orbit at its great distance forever, tracing the same enormous slow path around the sun, never once falling close enough to warm and glow. For a comet to be born, something has to disturb the body, has to reach into the cloud and change its path just enough to send it falling inward. And the forces that do this stirring are some of the gentlest in all of astronomy. None of them is sudden. None of them is violent. They work across thousands and millions of years with great patience. The most important of these forces is the pull of the galaxy itself. The Milky Way, the whole turning wheel of hundreds of billions of stars, exerts a faint and uneven gravitational pull on the outermost reaches of the solar system. It is a tide, in the same sense that the moon raises tides in the oceans, except that here it is the galaxy gently tugging on the far bodies of the sun's domain. This galactic tide is now thought to be the leading influence that delivers long-period comets inward. Slowly, across vast stretches of time, it reshapes the distant orbits, nudging some of them, until their closest approach to the sun creeps inward, year by year, until at last a body dips close enough to become a comet. The galaxy, in its quiet way, reaches into the sun's territory and stirs the pot. The second force is the passing of other stars. The sun does not sit still in the galaxy. It drifts among the other stars, and over long enough spans of time, other stars drift near it in turn. When a star passes close to the Oort Cloud, or even through its outer reaches, its gravity tugs on the bodies it passes. Most are barely affected, but some have their orbits altered enough to begin the long fall sunward, and so a passing star can send a slow trickle of comets inward, spread out over a very long time. These encounters are rare by human reckoning, separated by hundreds of thousands or millions of years, but the solar system is old enough to have seen many of them. The third force is rarer still. Now and then, as the sun travels through the galaxy, it passes near one of the immense clouds of gas and dust that drift between the stars, the same kinds of clouds where new stars are born. The gravity of such a cloud can also reach out and tug on the outer Oort Cloud, reshaping orbits and loosening bodies, much as a passing star would. What matters most for the feeling of all this is the pace. None of these forces is a catastrophe. They are slow, gentle, patient perturbations, acting across spans of time so long that, from a human point of view, the cloud appears perfectly still. The Oort Cloud is best pictured not as a frozen, unchanging shell, but as a reservoir that turns over so slowly that the turning is almost imperceptible, releasing the thinnest possible trickle of comets across the ages. It is the slowest stirring in the solar system, a motion measured in millions of years. The galactic tide deserves a little more attention because it is such a strange and gentle thing to picture. The sun sits within the broad disk of the Milky Way, surrounded on all sides by the combined gravity of countless distant stars and the dark matter that pervades the galaxy. This combined pull is not perfectly even. It is very slightly stronger on one side of the solar system than the other, and slightly different above and below the plane of the galaxy than within it. For the planets, close to the sun, this faint unevenness is utterly negligible. But for the bodies of the outer Oort Cloud, so loosely held by the distant sun. Even this whisper of a difference matters. Over millions of years, it slowly reshapes their orbits, tilting and stretching them, gradually working some of them into paths that dip toward the sun. The whole galaxy, in this way, gently kneads the outer edge of the solar system. It is striking that the dominant force delivering comets to our skies is not the sun and not the planets, but the galaxy itself. The grandest structure we belong to, the wheel of hundreds of billions of stars, reaches down to the scale of a single falling comet and decides, in its slow way, which bodies at the edge will begin their long journeys inward. When you watch a long-period comet cross the sky, you are, in a real sense, watching the influence of the entire Milky Way made briefly visible, a single body loosened from the edge by the patient pull of the galaxy and sent falling toward the warmth. The slowness of all this is the part most worth resting on. We are used to thinking of space as a place of violent events, of explosions and collisions and sudden change. The stirring of the Oort Cloud is the opposite of all that. It is the gentlest possible process, a faint tide acting on loosely held bodies across spans of time so long that nothing appears to move at all. A comet that falls toward us this year may have begun its inward journey 1,000,000 years ago, set in motion by a tug so slight it would be imperceptible in any single human lifetime. The cloud changes, but it changes at the pace of the galaxy, which is to say almost not at all on any scale we can feel. To picture the cloud is to picture patience itself, a structure that does everything slowly and nothing in haste. It can help to picture the cloud's slow turning the way one might picture the very slowest of tides, the kind that takes not hours, but ages to rise and fall. Nothing about it is sudden. A body whose orbit is being reshaped by the galaxy's pull does not lurch onto a new path. It drifts onto it across hundreds of thousands of years, its closest approach to the sun creeping inward by the smallest increments, until at last, after an almost unimaginable span of patience, it crosses the threshold that will send it falling sunward. By any human measure, the cloud is perfectly still. Its motion is real, but it unfolds so slowly that 1,000 human lifetimes would not be enough to notice a single body shifting its course. To rest in the thought of the Oort Cloud is to rest in the slowest motion there is, a turning so gradual it is indistinguishable from stillness. Part 11. The stars that pass in the night. The idea of a passing star nudging the cloud can sound abstract, so it helps to make it concrete with two real encounters, one recent and one still to come. Both can be held gently, because both are gentle events, despite how dramatic the bare description might first sound. Not so very long ago, in the timescales of the solar system, a small dim star is thought to have passed close enough to brush the outer edge of the Oort Cloud. It was a faint pair of stars, a small red dwarf with an even fainter companion, traveling together through the galaxy. For a while, this little pair was the closest star to the sun, nearer than any star is today. And it passed, by some reckonings, right through the outermost fringe of the cloud. It would be easy to imagine such a passage as a disaster, a star ploughing through our comet shell and flinging destruction inward. But that is not what happened, and the reasons are quietly reassuring. The passing star was small and low in mass, and it was moving quickly, so its gravitational grip on the cloud was weak and brief. Compared to the sun, even at that close range, its pull was modest. Most of the bodies it passed felt almost nothing. The models suggest it may have nudged some of the distant bodies, subtly altering the paths of a scattering of comets, perhaps sending a few of them on new long journeys inward across the ages that followed. And then the little star simply continued on its way into the dark, as quietly as it had come. Nothing was wrecked. The cloud absorbed the visit and went on turning. Looking far ahead, another small star is expected to make an even closer pass, this time deep inside the Oort Cloud, rather than merely brushing its edge. But this encounter lies more than 1,000,000 years in the future, almost unimaginably far ahead of any human concern. Unlike the last visitor, it is expected to be a gentle event. A small star moving past will not collide with anything, for the cloud is far too empty for that. It will simply tug on the bodies near its path, loosening a scattering of them over the long ages that follow, sending a slow increase of comets inward across a span of time longer than our species has yet existed. These two encounters, one behind us and one ahead, tell the same quiet story. The edge of the solar system is not a fragile or threatened place. The traffic of the galaxy does pass through it, but on timescales so immense that from where we sit, the cloud is essentially undisturbed. Stars come and go across hundreds of thousands and millions of years, brushing the cloud as they pass, and the cloud takes it all in stride, turning slowly, releasing its thin trickle of comets, otherwise unchanged. The visits are real, but they are unhurried, and there is nothing in them to disturb a quiet night. It is worth understanding why a passing star, even one moving right through the outer cloud, does so little harm, because the answer reveals just how empty the cloud truly is. We might imagine a star crashing through the cloud like a stone through a pane of glass, shattering everything in its path. But the cloud is far too thinly populated for anything like that. The bodies are tens of millions of kilometers apart, so a passing star would almost certainly never come close to a single one of them. Its effect is not collision but gravity, a gentle tug felt across the distance, slightly altering the orbits of the bodies it passes near. The star does not strike the cloud. It leans on it, faintly, in passing, and then it is gone. The brevity of these encounters also limits their effect. A star passing through the outer cloud is moving quickly, and the cloud is so large that the star crosses through its sphere in what amounts, on cosmic timescales, to a brief moment. There is only a short window during which the star's gravity can act before it has moved on into the dark again. A small, fast-moving star simply does not have the time or the mass to do more than nudge a scattering of distant bodies. The sun, by contrast, holds the cloud steadily and forever. In any contest between a brief passing visitor and the constant grip of the sun wins easily. The cloud belongs to the sun, and a passing star can borrow only the faintest influence over it before continuing on. There is real comfort in understanding these encounters properly, especially for anyone who has ever heard such things described in frightening terms. A star passing near the solar system sounds alarming, and stories sometimes dress it up as a looming threat. But the reality is calm. These passages happen across hundreds of thousands and millions of years. They do not strike the planets. They do not endanger the Earth. At most, over the long ages that follow, they may slightly increase the slow trickle of comets falling inward, a change so gradual it would never be noticed within any human span. The galaxy's traffic passes by the edge of the solar system, the way distant ships pass on a calm sea at night, seen faintly, if at all, leaving the water, in the end, undisturbed. It is worth setting these stellar encounters in their proper rhythm, because the rhythm itself is soothing once you feel it. Across the long life of the solar system, stars have passed near the sun many times, and will pass near it many times again. But the spacing between such passages is enormous, hundreds of thousands of years at the least, often far longer. From where we stand, in the brief flicker of a single human life, no such encounter is happening, and none will happen for ages. The next close pass lies far beyond any future we need concern ourselves with. So while it is true that the galaxy's traffic does reach the edge of the solar system, it does so at a pace so slow that, for all practical purposes, the cloud around us tonight is exactly as undisturbed as it was 1,000 years ago, and will be 1,000 years from now. The visits are real, but they are rare beyond rare, and tonight there is nothing passing but time. Part 12. The long fall inward. Let us follow a single body now, from its long sleep at the edge to its brief, bright life near the sun, because this journey is the one thread that connects the unseen cloud to the comets people have actually watched cross the sky. It is the story of how a dark, frozen lump at the boundary of the solar system becomes, for a little while, one of the most beautiful sights in the heavens. Far out in the cloud, a single icy body has been orbiting in silence for a very long time, tracing an enormous, slow path around a sun that is little more than a bright star to it. Then, gently, something changes. Perhaps the tide of the galaxy has slowly reshaped its orbit. Perhaps a distant passing star tugged at it ages ago. Whatever the cause, the body's closest approach to the sun has crept inward, and now its long orbit carries it down toward the inner solar system. The body begins to fall. But even falling, it is in no hurry. The distance is so immense that the inward journey can take millions of years, a slow descent across the entire breadth of the sun's domain. As the ages pass and the body draws nearer the sun, the cold begins, very gradually, to give way to a faint warmth. And at a certain point, the warmth becomes enough to change the body. The frozen gases on and near its surface begin to turn directly from solid ice into vapor, lifting fine dust with them as they go. A glowing envelope of gas and dust swells out around the small, solid core, growing larger and brighter as the body approaches the sun. This glowing head can grow to be larger than a planet, even though the solid body at its center is only mountain-sized. The pressure of sunlight and the stream of particles from the sun push the released gas and dust outward, away from the sun, drawing them into the long, faint, luminous tails that make a comet unmistakable. A body that spent untold ages as a dark and silent lump of ice becomes, for a few weeks or months, one of the brightest and most graceful objects in the sky. And then the comet rounds the sun and begins to climb back outward, and from this turning point, several different fates await it. It may simply retrace its enormous orbit, climbing back out toward the cloud, not to return for thousands or even millions of years, its single visit complete. It may, if it passed near one of the giant planets, have been deflected onto a shorter orbit, captured into the family of comets that return more often, its long exile traded for a closer, faster path. It may have been flung the other way, given a push that sends it out of the solar system entirely, to drift forever in the space between the stars, never to return to any sun. Or it may, over many passes, gradually use up its ices until nothing is left to glow, fading into a dark, inert lump once more, or coming apart into a stream of dust. What is worth holding on to, as the night deepens, is this. Every bright comet that has ever moved someone to stop and look up at the sky may be one of these travelers from the edge. A single body, loosened from the still and silent shell at the boundary of the solar system, making one slow visit to the warmth and the light before returning to the dark. The comets we see are messengers from the unseen cloud, the only part of it that ever comes close enough for us to witness. When you watch a comet, you are watching the Oort Cloud send a single quiet emissary inward across millions of years to round the sun once and go home. It is worth slowing down to picture the actual moment a comet comes alive, because it is one of the gentlest transformations in all of nature, even though it ends in such brilliance. For most of its existence, the body is simply dark and frozen, indistinguishable from a small, dark mountain adrift in the cold. Then, as it falls inward, and the sun's warmth grows from nothing to a faint touch, the change begins almost imperceptibly. A little of the ice nearest the surface begins to turn to vapor. A thin haze gathers around the body. Day by day, as it draws closer to the sun, the haze grows into a glowing head, and the first faint tail begins to stretch behind it. The transformation is not sudden or violent. It is a slow blooming, a frozen body gradually unfolding into light as it nears the warmth, like something waking very slowly from a very long sleep. The tales themselves are worth understanding because they reveal something quietly beautiful about how the solar system is arranged. A comet's tail does not trail behind it, like the wake of a boat. It always points away from the sun, swept outward by the pressure of sunlight and the flow of particles streaming from the sun. So a comet rounding the sun and heading back outward leads with its tail, the glowing streamer running ahead of the body rather than behind it. The tail is not a sign of the comet's motion at all. It is a sign of the sun's outward push, made visible by the gas and dust the comet releases. In the comet's tail, the invisible wind of the sun is briefly painted across the sky for anyone to see. And then the visit ends, as all such visits do, and the comet climbs back out toward the dark. Whatever its fate, whether it returns to the cloud, or is captured into a shorter orbit, or is flung from the solar system, or slowly fades to an inert remnant, its brief season of brilliance is over, and it carries its diminished self away from the light. There is a gentle melancholy in that, but a peaceful one. The comet does not mourn its return to the cold. It simply goes, as it has gone before, and may go again, a traveler keeping an appointment set in motion 1,000,000 years ago. And out in the cloud, 1,000,000,000,000 other bodies wait their own turn, most of which will never come. The few that fall are the only ones we ever know, and through them, briefly and beautifully, the unseen cloud reaches inward and touches the lit world where we live. Part 13. Where the sun's reach truly ends. The Oort Cloud quietly reshapes a question that sounds simple but is not. Where does the solar system actually end? It turns out there are two very different answers, two very different edges, and the space between them is exactly where the cloud resides. Understanding the difference is the clearest way to answer what hides behind the edge of the solar system. The first edge is the boundary of the sun's wind. The sun does not only give off light, it also streams a constant flow of charged particles outward in every direction, a thin, steady wind blowing off its surface and out across the solar system. This solar wind inflates an enormous bubble around the sun and the planets, pushing back the gas that drifts between the stars. Far out, well beyond the orbits of the planets, the wind finally weakens until it can no longer push against the surrounding interstellar gas, and there the bubble ends. That boundary, where the sun's wind gives out, marks one edge of the solar system. Humanity's most distant spacecraft have actually crossed this boundary, passing out of the sun's wind and into the space between the stars. By this first definition, the edge of the solar system lies not very far past the planets at all. But there is a second edge, and it lies vastly farther out. The sun's gravity reaches enormously beyond its wind. Long after the solar wind has given out, the sun's gravitational pull continues, holding bodies in orbit across immense distances. The true gravitational edge of the solar system, the distance at which the sun's hold finally yields to the broader pull of the galaxy, lies far beyond the boundary of the wind, out around 1.5 to 2 light-years from the sun. And that is precisely where the outer Oort cloud sits. Its bodies orbit right at this gravitational frontier, at the very limit where the sun's authority quietly fades into the galaxies. So the solar system has two edges, and they are nothing alike. There is the near edge, where the sun's wind stops, which our spacecraft have already crossed. And there is the far edge, where the sun's gravity stops, which lies thousands of times farther out. A spacecraft can leave the solar system in the first sense, crossing out of the sun's wind, and still have an almost incomprehensible distance to travel before it leaves in the second sense, crossing out of the sun's gravity. The Oort Cloud is what fills that immense gap. It is the long, dark outer territory that still belongs to the sun, even after the sun's wind has given out, the part of the solar system that lies past one edge, but well within the other. This is the literal answer to the question the night began with. What hides behind the edge of the solar system? The Oort Cloud hides in the space between the two edges. It lies past the boundary of the sun's wind, in what we often loosely call interstellar space, and yet it remains firmly within the boundary of the sun's gravity, still part of the sun's family. It is hidden in the gap between where we think the solar system ends and where it truly does. And that gap, it turns out, is by far the largest part of the whole. The two edges of the solar system are so different in scale that it is worth restating the gap between them in plain terms, because the difference is genuinely enormous. The boundary of the sun's wind lies a little beyond the planets, at a distance our spacecraft have already reached after a few decades of travel. The boundary of the sun's gravity lies thousands of times farther out. If the distance to the edge of the sun's wind were a single step, the distance to the gravitational edge would be a long walk of many hours. Almost everything we mean when we say the solar system, by sheer extent, lies in the immense space between those two boundaries, and that space is filled, faintly and invisibly, by the Oort Cloud. This distinction also clears up a common confusion about what it means for a spacecraft to leave the solar system. When our most distant probes crossed out of the sun's wind into the surrounding interstellar gas, it was rightly described as a historic crossing, a passage out of the bubble the sun blows around itself. But it did not mean the craft had left the sun's gravitational domain. Far from it. Those craft are still deep within the region the sun's gravity governs, and they will travel for many thousands of years more before they pass through the Oort Cloud and finally leave the sun's family altogether. They have crossed the near edge. The far edge, the true gravitational boundary, still lies an immense distance ahead of them. There is something quietly profound in realizing that the solar system is so much larger than the part of it we usually picture. We tend to imagine our cosmic home as the sun and its planets, a tidy arrangement we could almost hold in the mind. But the true solar system, bounded by the reach of the sun's gravity, is a sphere more than a light year across, and the planets occupy only its tiny luminous center. The Oort Cloud is the answer to where the rest of it is. It is the great dark body of the solar system, the immense outer volume that surrounds the small bright middle, hidden in the gap between the edge of the wind and the edge of the gravity, holding the sun's domain together all the way to its true and distant boundary. There is a gentle reframing in all of this for anyone who has ever felt that the edge of the solar system must be a lonely or final place. The Oort Cloud shows that the solar system does not end abruptly somewhere past the planets, with cold, empty, nothing beyond. Instead, it reaches outward, softly and enormously, holding its frozen bodies in the sun's keeping across more than a light year of space. There is no sharp wall where the sun's world stops and the void begins. There is only a slow, immense fading, the sun's domain thinning gradually outward until, somewhere in the dark, it quietly gives way to the galaxy. The edge of the solar system is not a cliff. It is a long, gentle shore, and the cloud is the shallow water that stretches out from it, farther than we ever imagined, before the true depths of interstellar space begin. Part 14. Other suns, other clouds. If our own sun gathered a shell of icy bodies in this way, born of scattered leftovers and lifted into place by passing stars and the galactic tide, then there is little reason to think the sun is unique. The same processes that built our Oort Cloud should have operated around other stars too. And so the models suggest something quietly wonderful. Oort clouds may be common throughout the galaxy, faint shells of frozen bodies surrounding a great many of the points of light we see in the night sky. This opens a few gentle ideas worth resting on. The first concerns the sun's own birth. The sun did not form alone. It was born within a cluster of sibling stars, all condensing together out of the same great cloud of gas and dust, crowded close together in their youth, before slowly drifting apart over the ages. In those early crowded days, the young stars passed near one another far more often than stars do now. And in that closeness, it is thought that the stars may have traded bodies. Some of the icy chunks in our own Oort cloud may have originally formed around other stars and been captured by the sun, while some of the sun's own bodies were given away to its siblings. If so, the cloud at our edge is partly a shared inheritance, a mingling of material from a family of stars long since scattered across the galaxy. The second idea concerns the present. Because the outer Oort clouds of different stars reach so far, more than a light year in some cases, the gravitational edges of neighboring stars' domains may not be entirely separate. Out in the faint outer reaches, the territory of one star may come close to brushing against the territory of another, so that the boundaries between the stars are softer and less distinct than we might imagine. The edge of the sun's realm may very nearly touch the edge of another's. The third idea is the most direct. Sometimes a body from another star's cloud comes all the way to us. Every so often, an object falls into the solar system on a path that does not belong to the sun at all, a path that is not a closed orbit but an open one, carrying the object in from the space between the stars, around the sun once, and back out, never to return. These are interstellar visitors, comets and bodies cast off from other stars' clouds, wandering the galaxy until chance brings them through our neighborhood. They can sometimes be recognized by their unbound paths, and at times by a composition subtly different from our own comets, hinting that they were made around a different kind of star. Only a small number of such visitors have ever been recorded, falling in from the dark, rounding the sun, and departing forever. But each one is a reminder that the clouds of different stars are not sealed away from one another. The galaxy quietly trades these frozen bodies across the immense distances, one rare traveler at a time. The takeaway is a comforting one. Our unseen shell is most likely not a lonely peculiarity, but one of countless such shells, scattered through the galaxy, around star after star. The Milky Way may be quietly full of these cold reservoirs, each one wrapped around its own sun, each one occasionally loosing a comet inward or trading a body across the dark. The edge of our solar system, faint and unseen as it is part of a pattern repeated across the whole galaxy. The notion that the sun was born in a cluster is worth dwelling on, because it changes how we picture the cloud's earliest days. Stars do not form one at a time in isolation. They form in groups, dozens or hundreds or thousands of them condensing together out of a single great cloud of gas and dust over a relatively short span. The sun was one such star, born among many siblings, packed far more closely together than the stars are spread today. In those crowded early times, close passages between neighboring stars were common, not rare. And during those frequent close encounters, while each young star was busy gathering its own shell of scattered icy bodies, the bodies could be passed back and forth between them, captured from one star by another, shared across the little crowd of newborn suns. If this picture is right, then our Oort cloud may be a genuinely mixed inheritance, holding bodies that formed around stars long since scattered to distant parts of the galaxy. Some of the comets that fall toward our Sun today may be made of material that condensed around a different star entirely, captured into the Sun's keeping in the crowded nursery of its birth. We would have no easy way to tell such a body apart from our own, for they would all have been made at much the same time, out of much the same material. But the possibility is a lovely one. The cloud at our edge may be, in part, a keepsake of the Sun's lost siblings, a faint shared memory of the family of stars among which the Sun was born. The interstellar visitors, the rare bodies that pass through the solar system on unbound paths, complete this picture in the present day. They are direct, current evidence that the clouds of different stars are not sealed off from one another. Every so often, the galaxy delivers one of these wanderers into our neighborhood, a body cast off from another star's shell, falling in from the dark, rounding the Sun once, and continuing on its way, never to return. We have recorded only a few of them so far, but their existence confirms that bodies like those in our own cloud drift between the stars, and that other stars must have clouds of their own to cast them off. When we watch such a visitor cross the solar system, we are watching a fragment of another star's edge pass briefly through our own, a quiet greeting exchanged across the immense distances between the suns. There is something quietly companionable in the thought that other stars keep clouds like ours. When we look up at the points of light scattered across the night sky, we are used to thinking of them as distant suns, each perhaps with worlds of its own. The Oort cloud adds another layer to that picture. Around a great many of those stars, in all likelihood, hang faint frozen shells, just like the one that surrounds us, each one invisible, each one holding its own trillion bodies of ancient ice, each one releasing its own slow trickle of comets into its own small system. The galaxy, seen this way, is not only a scattering of suns and worlds. It is also a scattering of these cold, quiet shells, one wrapped around star after star, a shared and repeated feature of how stars and their families are made. Our unseen edge is one of countless unseen edges, and in that there is a gentle kind of belonging. Part 15. Why we have never seen it. Now we come to the second half of the question the night began with, the quiet question of why, with all our telescopes, we have never managed to see this enormous shell at all. After everything we have learned about it, its shape, its size, its bodies, its origin, it can seem almost strange that it remains entirely unphotographed. But the reasons are simple, and once understood, they settle the matter completely. There are two of them. The first reason is the relationship between size and distance. An individual body in the Oort cloud is small, roughly the size of a single mountain, while the distance to it is enormous beyond easy comparison. The ratio between the two is so extreme that finding one of these bodies is far harder than finding a needle in a haystack. A telescope trying to see an Oort cloud body would be attempting to pick out a single mountain at a distance tens of thousands of times greater than the width of the entire planetary system. There is simply not enough there, at that range, for any instrument to resolve. The bodies are too small, and the gulf to them is too wide. Even the most powerful telescope finds nothing to fix upon. The second reason is even more fundamental, and it has to do with light. We can see stars and galaxies across unimaginable distances because they shine. They generate their own light and pour it out into the universe, so that even from billions of light years away, their glow reaches us. The planets do not shine on their own, but they are close enough to the sun to catch its light and reflect it back to us, which is why we can see them in the sky and study them through telescopes. The same is true of the asteroid belt and even the icy ring beyond Neptune. They are near enough to the sun to be lit by it. But the Oort cloud lies so far out that the sun is no longer a source of meaningful light to it. Out there, the sun is just one more star among many, far too distant to illuminate the dark bodies in any way we could detect. The bodies make no light of their own, and they receive almost none to reflect. They are dark objects against a dark background, and there is simply nothing for a telescope to catch. So our knowledge stays indirect, and likely will for a long time to come. We see the Oort cloud only in the comets that fall out of it, and in the careful mathematics of their orbits. We read it rather than view it. And there is no shame in that, for science has often done exactly this, accepting and trusting things it could not directly see, reasoning instead from consistent, indirect evidence. Long ago, the idea that the planets circle the sun, rather than the Earth sitting fixed at the center of everything, was argued not from any direct picture, but from the patient study of how the planets moved across the sky. No one could step back and photograph the arrangement. The idea held because the evidence was consistent and the reasoning was sound, and in time, it proved entirely correct. The Oort cloud sits in that same honest tradition. We believe in it because everything points to it, steadily and from many directions at once, even though no eye and no instrument has yet rested upon it. It is known without being seen, and that is its own kind of quiet marvel. It is worth appreciating just how faint these bodies are, because faintness, even more than distance, is what defeats our telescopes. We are able to see some genuinely remote objects, after all. We can image galaxies billions of light years away, far beyond anything in our own galaxy, let alone our own solar system. The reason we can see those distant galaxies and not the much nearer Oort cloud comes down entirely to light. A galaxy is made of hundreds of billions of stars, each one a furnace pouring out light across the universe. An Oort cloud body is a single dark mountain of ice that generates no light at all and receives almost none to reflect. It is not the distance alone that hides the cloud. It is that there is nothing there to shine. We can see across the universe where things are bright, and we are blind to what sits much closer when it happens to be dark. This explains a small irony worth noting. The Oort cloud is, in a sense, in our own backyard, part of our own solar system, immeasurably closer than the distant galaxies we photograph with ease. And yet it is invisible to us, while those galaxies are not, simply because the galaxies blaze and the cloud does not. Nearness counts for nothing if there is no light. The cloud could be 100 times closer than it is, and we still could not see its dark bodies, for they would still make no light and reflect almost none. Distance is part of the difficulty, but darkness is the heart of it. The cloud is hidden not behind a great distance alone, but behind its own deep and permanent night. That our knowledge remains indirect is not a weakness in the science. It is, if anything, a quiet triumph of it. To know with confidence about a structure no one has ever seen, to map its shape and size and origin from nothing but the paths of falling comets and the logic of physics, is a remarkable thing. It is the same kind of reasoning that has let us understand a great deal of what we cannot directly observe, from the structure of distant worlds to the makeup of the early universe. The Oort cloud reminds us that seeing is not the only way of knowing, and often not even the most powerful. We have come to know an invisible shell more than a light year across surrounding everything we are, and we have done it without ever once laying eyes upon it. That we can know such a thing at all is a gentle wonder worth carrying into the dark. Part 16. The quiet shell around us. And so we come, at the end of the night, back to where we began, to the faint, enormous shell at the edge of the solar system, but now with the whole of it gathered in the mind. We know its shape, a flattened inner region blending outward into a great spherical shell. We know its size, more than 1.5 light years across, the largest thing the Sun holds. We know what it is made of, 1 trillion mountains of ancient ice and dust, each one alone in the dark. We know how it formed, from the scattered leftovers of the planets, lifted and held by the gentle pull of passing stars and the tide of the galaxy. We know what it does, releasing its slow trickle of comets inward across the ages. And we know why we have never seen it, too small and too dark and too far for any light to reveal. It is worth holding the whole picture for a moment as the night settles. The Oort Cloud is the outermost boundary of the only home our solar system has ever had. It is so wide that a spacecraft would need tens of thousands of years to cross it, so faint that it has never once appeared in an image, so cold and still that its bodies have not changed since the planets were young. Most of the time it does nothing at all. It simply holds its place in the dark, turning with a slowness beyond imagining, keeping the frozen memory of the solar system's beginning safe at its rim. And every so often, gently, it lets a single comet fall inward toward the light, a quiet emissary from the edge. Think back over the journey the night has taken, because it traces the very way the cloud was discovered. We began with the planets and the 2 belts we can see, the familiar lit ground of the solar system. We followed the strange comets that arrive from every direction, falling in on orbits thousands and millions of years long. We read in those orbits the signature of a distant spherical reservoir, and from that reading, the cloud took shape in our understanding. We pictured its form and its enormous size, its frozen mountain-sized bodies, its birth from the scattered leftovers of the planets. We watched it stirred by the patient tide of the galaxy and the passing of distant stars, and we followed a single body on its long fall inward to bloom briefly into a comet. We found the true edge of the Sun's reach far beyond the boundary of its wind, and we saw that other stars likely keep such shells of their own. And we understood, at last, why the cloud stays hidden, too small and too dark, and too far to ever catch the light. The whole night has been a slow walk outward, following the evidence step by step, just as the discovery itself once moved outward from the comets to the cloud. What lingers at the end of that walk is how much can be known about a place we will almost certainly never visit and have never even seen. No one alive will travel to the Oort Cloud. No spacecraft we have built will reach it for thousands of years. No telescope we possess can show us a single one of its bodies. And yet, we can speak of it with real confidence, describing its shape and reach and contents and history, because the universe leaves its traces even where it hides its face. The comets carry the cloud's existence inward to us, a little at a time, and patient minds have read those messages and reconstructed the unseen whole. There is a thought to carry into sleep in all of this. An edge we cannot see is not a thing to fear. The unseen shell at the boundary of the solar system is not a void waiting to swallow us, and not a wall pressing in from the dark. It is a calm outer boundary that has surrounded and sheltered the worlds for more than 4 billion years, asking nothing, threatening nothing, simply being there. We did not need to see it for it to hold us. It has wrapped the solar system in its faint, enormous sphere since long before there was anyone here to wonder about it, and it will go on doing so long after this night is forgotten. So let the edge of the solar system be a comfort tonight, rather than a mystery to solve. Picture the bright, familiar middle, the sun and the planets, held safely at the center of that great, gentle shell, the way a small light is held within a wide and quiet dark. There is an edge out there we have never seen, far beyond the farthest planet, turning slowly in the long calm between the stars. It has always been there. It will be there in the morning, and it is keeping watch over the solar system, whether or not anyone is awake to know it. Let your breathing slow. Let your thoughts drift outward, past the planets, past the icy belts, all the way to that faint and peaceful shell, and let them settle there in the quiet. The edge of everything is calmer than you might have guessed. Sleep well, and good night.